and welcome back again. I want to look at another parametric test called three-way repeated measure ANOVA. Three-way repeated measure ANOVA. If you understand three-way ANOVA, okay, and you have a little bit understanding about pair t-test, you have no problem. If you have not watched that, you can go and watch that in the videos from the teaching class, from the lecture so far. You can understand what three-way ANOVA is and what pair t-test is. In this case, we are looking at dependent variable or dependent groups, all right, on continuous variable. Okay, the effect of dependent variable, which is categorical variable now, all right, dependent categorical variable on continuous variable, for that is for a repeated measure, all right. But when you look at ANOVA, it's directly talking about independent groups on continuous variable or continuous outcome. Simple. That's just different. Because in here, in the repeated measure, we are following paired t-test concept. Right? The same individual is tested repeatedly. First time, second time, and third time. The same individual. All right? That is called dependent groups or variable down. But it is different from normal ANOVA. That is independent variable. All right? On continuous variable. So you can have a gender, you can have colleges or departments. They are both independent variable. All right? Maybe on the score of students. Okay, that is under three-way ANOVA, for example. You have many categorical variables like that on the score. They are not dependent, right? They are just like that. But under this particular one, this is dependent because you are measuring the record of one subject or one specimen repeatedly many times. Okay, and at different times there is always a different period in time. So this is very important. This is why make it repeated measure. So here we are going to look at three groups, actually three categorical variables here under three-way ANOVA. One of them, at least one of them, will be three groups. When I say three groups, the other two may not be three groups. All right, you may have two, but at least one of them will be three groups. So if you remember two-way ANOVA, repeated measure ANOVA we did the other time, one is having two groups from the categorical variable, another one is having three groups. For example, we have maybe treatment, and we have diet and control, that is two groups under one. Then we have time, T1, T2, T3. So that is two categorical variables, but we having one having two groups, one having three groups. That is under two-way repeated ANOVA. But under three-way, we having three categorical variable now. One may have three groups, T1, T2, T3. All right, we may have something like maybe diet also, and more other variables to support it. All right, so that is that. So let's see how it goes now. When we are talking about the repeated measure ANOVA, generally they are used for analyzing data where same subjects are measured more than twice. All right, that should be clear now because I've done that many times now when I'm dealing with other ANOVA repeated measure in the past. So that should be you have more understanding now. So this test is also referred to as within subject ANOVA or ANOVA with repeated measures. The within subject term means that the same individuals are measured on the same outcome variable under different time points or conditions. The same individuals. Okay, that is why I make it within subject. Okay, we know we have between subjects, so that is different from this. So three-way repeated measures ANOVA used to evaluate simultaneously the effect of three within subject factors on continuous outcome variable. Now this time around three if the effects of three within subject factors, right? You have three categorical variables. That's what it means. Three categorical variables, all right, on a particular continuous variable. That's what it means. All right. So that should be clear. Which means you are talking about independent variable on dependent variable. That's what we're talking about now. All right. So we have some assumptions as usual. They follow the same assumption. Dependent samples. The sample must be dependent. All right. That's the usual assumptions. And normality, the data should be approximately normally distributed and have metric scale level, which is why it is continuous in the first place. All right, it's measurable, must be measurable with units. This assumption is specifically important when the same size is small, when the sample size is small rather. So if the sample size is more, then you may not, you may try to probably depreciate the standard of normality, or probably you can just you may skip if other assumptions are met. All right. Okay, so homogeneity of variance is there. The variance in each group should be equal. Levin test can be used for this. Why you can use Shapiro for this? And the homogeneity of variance for covariance now. Homogeneity of covariance now. That's sphericity. The variance of the difference between all combinations of the groups should be equal. All right. So this assumption is tested using a Matchley test or sphericity. Okay. So this one will automatically be seen when we run our ANOVA. So no extreme outliers. So we don't need too much outliers. So when you have to test for extreme outliers, the difference between outliers and extreme outliers, they're not the same. So you have to carry out a test to show that this outlier is not extreme, right? We are going to do the test, which we have done before on that two-way. So we are going to repeat it again to see. Then data, let's go at data and research direction. The main goal of three-way repeated ANOVA measure ANOVA is to evaluate if there is a statistically significant interaction effect between three within subject factors in explaining a continuous outcome variable. That is what I explained before. I'm looking at an interaction effect between three within subject variable, between categorical variable. That's what it means in explaining a particular continuous variable. All right, three independent variable. All right, in explaining a dependent variable. So we use the weight loss dataset in the Ethereum package in this study. We wanted to assess the effect of diet exercises on weight loss in 10 sedentary individuals. And so we want to look at the diet exercises. Diet is a categorical variable, exercise is a categorical variable, all right? And they want to look at it with time, okay? So the weight loss is our data set actually. So the participants will enroll in 4 trials. We have no diet, and no exercise, that's one. Diet only, exercise, that is another 2. Exercises only, and number 4, diet and exercise only. Which means this particular diet categorical variable column is having 2 groups, yes and no. This exercise also is having 2 groups, yes and no. That's what it means. Now, here, under here, we have no diet, no exercise, which means no, no here, no here. Now we have another one, we have diet only, all right? So here you have no, here you have yes, that's what it means. Okay, diet only means here we have yes, here we have no, right? Here exercise only, maybe you have yes here, you have no here. Here, diet and exercise, we have yes, yes, here and here. That's what it means. So each participant performed all 4 trials. The order of the trials was counterbalanced and sufficient time was allowed between trials to allow any effect of previous trials to have dissipated. Okay, each trial lasted 9 weeks and the weight loss score was measured at the beginning of time 1, okay, at the midpoint time 2, and at the end time 3 of the trial. So we have a T1, T2, T3, another categorical variable, which is the third one. So don't forget, we have diet, we have exercises, and we have time. Okay, so don't forget that. So we have 3 categorical variable now. So this one is having 3 groups, T1, T2, T3. Why effect? Why diet is having two groups and exercise is having two groups. All right, so take note of that. So, but we are looking at a time will be our a focal point now. So this research is conducted to determine whether there is a significant interaction between diet, exercises, and time on the weight loss score. Okay, so we have a factor now. Our factor variable now is we are looking at them now on the response variable now, which is a weight loss or outcome now. Outcome is weight loss. That is our score, be the score, right? So what will be the effect of an interaction of these three components: diet, exercises, and time? All right, so we're going to run our datardium again. Okay, inside it we have weight loss. Okay, we have weight loss. We also have we'll have to glimpse it. Let's glimpse it and see what we have inside the data set. So we have ID as usual. This ID for individual people, 1 to 12, right? Then we also have a diet. Okay, so which is a yes and no. We also have exercises, which is factor variable also, yes and no. Don't worry, we have three factor variable. We have this, and this. Don't forget, this one is a factor variable as well. Don't forget. All right, so we're going to convert it later to score. Okay, where you have T1, T2, T3 as your time. All right, so don't forget that. So you can actually deal with it like this also, but it doesn't make sense. So it will be an issue. So because of the way the data comes, so you have to group this one together, all right, so that you can have your score and separately and have your time as a category variable separately. So this score for each of them, I mean weight loss score. All right. So now let us view it in form of a wide format. So we can just run this line of code and view it in a wide format, diet scores. All right. So now we have ID here, we have diet here, right? We have exercises here, we have T1, T2, T3. So what I'm going to do now, we're going to adjust this T1, T2, T3 and make it time. Then the score will be under score, all right, so that you can have two more variables added to it. So now, so we want to combine now. So let's run this statistics now. So we run this line. So we say our weight loss, we call it our weight loss. We say gather key time value is how to score T1, T2, T3. So when we run this, now. So now we have done that. So we have combined it together. So we can now check we can glimpse again now. So now our ID remain our ID, diet remain diet, exercise remain exercise. But time has been given to T1, T2, T3 now, and score for each one has been recorded. So we have this like this, like this. Okay, we have this and this, this and this, this and this, this and that's what it means. That's what we had before, but we have rearranged them properly now. So we can look at maybe 30 set of data. So, or let's just look at it from a view. So here we have 1 to 12 for the first person, to the first person, the second person, third person, fourth person. So first set. Then again, the same individual was repeated again, 1 to 12 again. Right? The same individual was repeated again, 1 to 12. The same individual by 1 person, by 2 person, by 3 person. So this is called repeated measure. All right. Okay, so that is what we are talking about. So we can close this. Now, in this example, now the effect of the time is our focal point. Now it's our focal variable. That is our primary concern. Effect of time. You can use them interchangeably, making maybe you can isolate time and use a exercise and a diet. You can also isolate exercise and use a time and exercise. You can isolate exercise again and use diet and time. You can make anyone you want to make your moderator now depend on individual based on what you are looking for. All right. So, but our focal point now is time. It is thought that the effect of time on the weight loss score will depend on two other factors, which is diet and exercises. Right. The effect of time on the weight loss, so will depend on the diet and exercises. Right. How long you diet and how long you exercises. Right. So the effect of time will depend on what the weight loss. So that will determine how much weight you have lost. okay, or how much weight you have gained. Okay, yes, it could be, you could gain, you could gain a weight also while you are also preparing to lose weight. Okay, depending on what you are consuming. All right. So which are core moderators now? So these two are core moderators now. Okay, based on what you are trying to observe now, what you are looking at now. So this one can also become maybe if diet is your focal point, for example, this and this will become your moderator variables. Or if the sizes is your focal point, then time and diet will become your moderator variables. So that now depend on individual what you are looking for. So but we want to focus on time now on the weight loss. So let's create some plots and see how it look like graphically. So we want to pass our weight loss in GG plot. Then we do exercises here as our exercises. Then our score is y. That is our numerical variable now. Then we can fill with time so that we can see T1, T2, T3, and then we can now make it a facet trap for diet so that we can now see them differently. Okay, let's just run this. So you can see here, right? You can see the structure here. I look like. But you can also plot another one here to make it more clearer using a GG box plot. Okay, so let's also look at this, right? I think this look more clearer, right? So let's zoom it. You can see we have a time. This color is time. T1, T2, T3. T1, T2, T3, T1, T2, T3, T1, T2, T3, and so on. So we have a diet. This diet now, we are looking at this diet column. This is a diet. We have no, this yes. Diet have no and yes. Okay, diet for no, and then we have exercise here. No, yes. Exercise, no, yes. So we have diet here. So when exercise, no exercise here. Under no exercise for diet, we have outlier for T1, outlier for T2 as well. Two outliers here, one here. Okay, and under diet for under diet no for diet, we have no exercises outlier for T3, one. So you can see that. So this facet make the work more easier for you to understand because of the complication of the plot. So we can it's better we use facet to split it so that I can see clearly what is happening. So that's why we use this plot. So this what is it make it clearer. It contains a lot of information. All right, information. So that is that. So let's move on quickly and compute some summary statistics and see using weight loss as a score by groups. Then we diet. Our groups are diet, exercise, and time. So we want to look at the mean and standard deviation of them. So we pass our weight loss using our 30 verse now. So I'm talking about our piping rather. So piping, we group by diet, exercises, and time. Okay. So when you're grouping now, we're grouping by 3 factors now. Okay. Before under 2 way repeated ANOVA, we group by 2 factors. Right? Don't forget. So now 3 factors now, and we are getting the summary. Okay. So that summary of score. Okay, which is both mean and median. So if we run this now, you have this. Okay, we have diet, we have exercises, we have time, we have variables called that variable we use the number 12 for each. This one is a balance variable distance. So we also have unbalance. So we don't want to go there for now. So so we have mean, we have SD. Is any mean that is the same here? Look at it. We have 11.6, 11 points. So none of them is the same. They are all unique. You have unique mean. Unique. You can see that they are all unique. They are different. All right. So that is that. So let's now go further and see, check our assumptions. So the first assumption I want to look at is outlier assumptions. Is there any extreme outlier? We have seen that there's outlier now. Okay. It's obvious from this plot that there's outlier. But I want to know, is this extreme? We need to confirm. Merely doing it, it's not extreme now. Okay? It's very clear from the plot that the outlier here is not extreme. Okay? Or the outliers are not extreme. Okay, so we can confirm that by doing a proper testing. So we run our weight loss here, we pass our diet, exercise, and time as a group here. Then we use the function identify outlier score based on these three groups. So we run this, we code, okay, just click here and run. So diet, exercise, time, ID, we have a score. It's outlier, say true. It's outlier. So let's extend this a little bit so I can see clearly. Let me run again. Okay, it's outlier, they're true. Each of them are, we are going to, in the combination there's outlier. But is it extreme? No, false, not extreme. So that is clear. Then let's check normality now. Using Shapiro, we are going to pass by group, diet, exercise, and time. Okay, so let's run this with loss. Just run this now. So want to see. Okay, so look at it now. For p-value, we have 0.2, 0.2. So you can see all of them pass the test. Every one of them is greater than 0.05. You can see, so you all pass the test in combination. Okay, so all right, let's continue. So here the weight loss score was normally distributed, okay, as assessed by the Shapiro Wilkie test of normality. P is greater than 0.05. Okay, so now all of the P are greater than 0.05. Okay, so that is what we have done so far. So that is clear. Then we can also do QQ plot for each cell of design. Okay, we can do a QQ plot to see. All right, so this one is a complex QQ plot actually. So because it's having a lot of components here. So we have weight loss, our cerebral capacity here for QQ plot. We have our score. Okay, we just use this team to make it clear. This team make the background white a little bit so that they can see clearly. Then we use facet grid. So we use diet plus exercise with time. So we label both. So when we run this now, you should be able to see our facet. Now, if you let's zoom out and see. So you can see the QQ plot this time T1, T2, T3, and we have a diet here, no, diet yes, diet yes, diet no. So diet no, no, yes, yes. Then under no, we have no, we have exercise. They could have been combined together as no. This one as yes, but because we are breaking it here, so that's why. So exercise no, exercise yes, exercise no, exercise yes. You can see this very clear and well explained diagram. Okay, so we can have it like this. So you can see the outlier is under 2. You can see that the data lines along the line. So there's no extreme outliers using QQ plots. All right. So it's just very clear. So we can go ahead with our computation of a 3-way repeated measure ANOVA, repeated measures ANOVA. So now let's compute now. Let's say we have a result which is result equals to ANOVA test data is weight loss. Our dependent variable, don't forget DV means dependent variable, our score, okay, and our independent variable are diet, exercises, and time. So that's called within factor. That's what we call within factor. They are independent variable in this concept. So in this context, so now we can run this now. So we have 3. That's why we pass 3 here. So let's say we run the result. So we now say get ANOVA table now result to see what we have done. So let me just zoom this out, run this again. All right, so this is what we have. We have effect, we have a degree of freedom, we have degree of freedom 2, we have a F here, we have p-value here, we have JES. Okay, this JES is actually for the sphericity. Okay, measure the sphericity of the data. So you can see that only this diet and this one that are not emitting the diet and time here, and not emitting the assumption. Okay, and this one. So others the meet assumption for sphericity. Right, so because this one is less than 0.05, this one also less than 0.05, all right, but others are not. So that's okay. So at least we met the assumption for homogeneous and uh, uh, outliers and Shapiro. So we have a single effect here now, single effect, which is diet significance. Okay, this p-value, all of them are significant actually. All right, exercise time, and we also have a interactive effect here, right? So they are all significant. All right, so from the result now, it can be seen that there is a statistically significant three-way interactions between diet, exercise, and time. All right, very clearly. So you can see from this type 3 test. All right, so that is what we have at hand. Very significant three-way, two-way diet. Okay, two-way diet, exercise, interaction. So we have two-way this and this, which is significant here, and the two-way exercise and time significant. Meanwhile, the two-way diet time interaction was not statistically significant, which is this one. This one. This one is significant. This p-value. Let me see. This one. It's not significant, right? But others are significant, right? Others. The single effect is significant. Interactive effects, they are also significant except diet and time. Right, that's what I was saying. So you can see the not significant. Right, so let's do some post-hoc test. First one, we want to compute simple two-way interaction. So we are actually free to decide which two variables will form the simple two-way interactions, and which variable we add as the third, which is our moderator variable. All right, so in the following code now, we have considered the simple two-way interaction of exercise and time at each level of diet. So let's group the data by diet and analyze the simple two-way interaction between exercises and time. So we are going to group by diet, then we are going to interact between exercise and time. So let's say we group by diet now. So we now want to rerun again our ANOVA. We want to our score. The variable is here, the same thing we are still pass here, but now we are using within and time. So this is just what you have done before in two-way ANOVA, right? That's exactly what we are doing now, two-way ANOVA again. So this is what to just to find out. Okay. So you can run this now. So you can see here, this is just two-way ANOVA effect. So this one, you may not necessarily need this actually. All right, so you can see here now that these are all significant except this one. Okay, so you can see this one is 9.9, 0.9, 0.09. All right, so we are having, that is a exercise and time interactive effect. Okay, so there was a statistically significant simple way two-way interaction between exercises and time for diet no trial. Okay, diet no trial, and but not for diet yes trial, right? Diet yes trial. Okay, it's not significant. All right, so what is the value here? So we have a 0. Diet yes trial, not significant. Okay, so that's for the interaction. This is it now. So it's not significant. So we want to also look at a pairwise also. All right, pairwise, and they want to look at a multiple pairwise comparison to determine which group means are different among them. So let's group the data by diet as well again, and exercise. Want to group data by data and exercises and perform pairwise comparison between the time points using Boolean adjustment. So we can use other adjustments. So if you want, so let's compare. We're going to pass our weight loss again. So we group by diet and exercises. So our focus is time. So don't forget that. So we are going to perform it. So we want to you don't want too many details. We want to remove degree of freedom and statistics. So we run this code. So then we can now filter. So let's filter and show. Actually, you can actually run this, okay, only this one, and see what you have. But there are too many information here, so we don't need all of them, right? So we don't need all of them. So we can actually let's just filter it. We are going to see the few things we need here. So let's remove and also remove p column, which is this one. We only need p adjusted value, right? So we don't need p, and p means p value. So but we need p adjusted. That's the purpose of the pairwise. So in the pairwise comparison table above, we are interested only in the simple comparison for diet, no, exercise, yes, groups report. So that is what we are interested. So that's why we use this. All right. So we are now we are having this important. So they are all significant at even at a adjusted p value of a Pomferoni adjustment. So we could report this as follows: that all pairwise comparison were run between the different time points for diet, no, exercise, yes, trial. The Bufferoni adjustment was applied. The mean weight loss score was significantly different in all time points comparisons, which when exercises are performed. So we're using p less than 0.05. So in this example, there are three possible combinations of group differences. However, it now depends. Okay, it depends on our interest. So you can interchange them. Okay, depending on our question at hand, you can interchange them. So this is just for three-way repeated ANOVA, measure ANOVA. All right, so I hope you enjoy the class, and I will see us in the next class. Thank you so much. Bye for now. If you are not subscribed yet, you can go ahead and do that, and to see more of the videos.